is lecture number 27 E524 Digital Mos LSI circuits, and today is October 26, 2020. Previously, we were studying sequential circuits. In sequentials, we have studied something called the static latch and flip-flops, right? For flip-flop, we have, like in latch, we have studied positive and negative latches, and also using the master-slave approach, we have made the flip-flop. We know that the latch is the one which is level sensitive, whereas flip-flops or the resistors are age triggered, right? So we studied all these things, but we have not moved to something called dynamic. Dynamic is the one, means dynamic latch, or you can say flip-flop, are the one where the data is dynamic or it's moving and it's not stable. I would say that you need to keep the data in terms of like less than milliseconds, whereas in the case of and flip-flops are very popular in the design of processors, right, where the refresh of the data is required maybe less than millisecond. It might be microseconds also, or even lesser than that. But in that case, you need the dynamic latch or the dynamic flip-flop. Notably, one should understand that the capacitor is the one which can store the data. Right? So this capacitor will be used to store the data, and afterwards you can use it wherever it requires. So this will be the most important part for the dynamic latch or a dynamic flip-flop. So let's assume that the first circuit, which is very popular, let's say there are two parts are there. First one is negative latch, and second one is positive latch. You can see here, this is the transmission gate. When clock equal to 0, I know that this particular thing is actually, this yellow line is going to be activated, whereas this particular transmission gate is going to be off. So the data is not going here at that time. Whereas when clock equal to 0, I know that whatever that will be stored on the positive plate of the capacitor, and later on, if it is logic 1, it will be connected to logic 0, and if it is logic 0, it will be connected to logic 1 because of this inverter, right? And thereafter, when you know that the clock equal to 1, then during clock equal to 1, this negative latch is going to be off, and negative latch will be activated over here, right? So in that case, you can have the data at the output, whatever you sent as D, that will be available at the output. Notably, this is the positive age. You can see here the data has to be ready before this inverter. In that case, the setup time is going to be equal to, so this will be the setup time, which is of propagation delay of transmission gate. Whereas in the case of contamination delay, which is involving after the setup time, that will involve two propagation delay of inverters and the propagation delay of the transmission gate, right? And the as you know that the requirement of hold time is remain same as as ideally it's 0. That was the case of previous circuits also. Note that here when you are making this, we are not having anything like a circuit which was like this. We are not keeping it right now at the beginning. However, if you wish, you can keep that just for the better functionality. And when you are making this, it's similar thing which we were doing for the previous case. And when you are doing this, you have to make sure that this particular loop will be weak inverter. This has to be weak inverter, and this has to be strong inverter. Now the meaning of strong inverter and weak inverter remains same. It says that when strong inverter is there, the resistance is low, and weak inverters are there, resistance is actually very high. So in the feedback, if there is a reverse conduction is there, these things will take longer time, and you won't have the disturbances coming from this reverse conduction. So that's why we are doing all this thing, and it's depending on the impedance looking at a particular side. Notably, this capacitor C1 and C2, which has been taken over here, it's taken with the fact that this side it's inverter, and this side I'm taking as transmission gate. So D actually is not there, but we are considering that at this node, what are the capacitances? So at this side, you will have the diffusion capacitances coming from these two transistors. Other than that, the input side, there are the gate capacitance and the overlap capacitance will be there. So all those capacitances in total are going to be here. So the capacitance looking this side, so the capacitance of transmission gate and capacitance of inverter. Adding all the capacitors will be the bigger capacitor over here. So that capacitor has been kept over here. Just for the simplicity, there is one capacitor, but you can take your own value also. But in that way, if you are increasing the capacitor, the required time to charge and discharge will decrease. You can understand that the combination of this transmission gate, the resistance of the transmission gate, and the capacitance of this one is going to decide how much propagation delay will be there. So that if you want to reduce it, C1 has to be as low as possible, or as per the requirement, and resistance also has to be as low as possible. And the combination of RC has to match your required clock rate and the input data. The clock rate as well as input data. But notably, clock rate is not only depending on this RC, but it's also depending on the required setup time, hold time, maybe sometimes jitter, right? And maybe the contamination delay. So all these together is going to decide the clock rate. And this is very standard question people are asking. You have to find out you have to propose a clock rate on the basis of the propagation delay by each of the stage. Now, there might be the case that there are clocks which are like this. By the way, this one is known as 0-0 overlap, and this one is known as 1-1 overlap. What does it mean? This clock and clock bar are actually overlapping each other. So the best way is you can take the non-overlapping clocks. However, if you cannot avoid such situation, then there are different possibilities are there. And the most of the time, like the problem is 0 0 overlap or maybe 1 1 overlap, right? So let's assume that even if you are giving non-overlapping clocks, but still there are I would say that there are some overlap in the logic 0 and overlap between logic 1. So in that case, what to do, right? Because what is happening when clock is 0, clock bar is also equal to 0. Let's take some situation like this. In that case, look, this particular PMOS is going to be on, and here this PMOS is also, right? And okay, so clock equal to 0, so it's going to make this one also on, right? And this is a mistake over here, because clock bar will become 1, right? And here clock equal to 0, so this will both are exactly equal. So in that case, like right now, this is the case when only this one is appearing, but let's assume that there is a case when clock and clock bar both are giving 0. So this is also 0, this is also 0. So in that case, all the PMOS will be on, and these are going to make these transistors in off state. So they are in the off. Red color indicates they are off, right? Because clock and clock bar both are 0. So right now there is a direct transparency between the D to Q with the available propagation delay. So when such things are there, there is one possible thing is if the 0 0 overlap is much lower than the propagation going from input to output. What does it mean if T overlap 0 0 is less than time or the propagation delay of T1, propagation delay of I1, propagation delay of T2? Altogether, if it is less than 0 0 overlap, you are in the safer side. No problem. That will not be transmitted at the output side. However, if it is greater than that one, means overlap 0 0 is more, means this value can be transferred over here, right? And similarly, if you are looking at the whole time, the input has to be hold. So by looking at this diagram, you can understand that after getting the value, it has to be hold by more than overlap by 1 1. Here you can see when it's 1 1, when clock and clock bar are 1, this thing will be flipped, and PMOS are going to be off, whereas NMOS are going to be on, right? And when there is clock equal to 1 1, we have to make sure that afterwards, because this clock equal to 1 is the one when we want to take the input going from 0 to 1, as it is positive age triggered, I want to sample the data. So in that case, I need to make sure that my output should not be changing at least before this T overlap time, and my hold time has to be greater than T overlap, such that the output does not take any faulty input. Okay, so if you want to remove this, such condition or such kind of situation can be avoided by a technique called Square Mos, because of we are using clock skew based approach. It's known as Square Mos. Notably, one more thing I forgot to tell you over here. Such kind of situation when clock and clock bar overlapping, it's known as the clock skew. This is one thing. So whenever clock skew is happening, you can avoid with the next technique, which is C-square Mos. Such kind of thing is also known as race around condition. Because race around means D, with changing of D, Q is also changing. Look, it does not matter whether you are taking sampling from 0 to 1, 1 to 0. It will not sample only one value, as there is direct path from D to Q. The output is going to be changing with respect to D input, and that is known as the race around condition. So race around is happening because of the clock skew. Clock skew means overlapping of clock and clock bar. So I want to remove that. So one technique says that if such kind of arrangement, so first one was master, the second one is the slave, and this technique we are going to call it C-square Mos. So this is C-square Mos technique, which is clock insensitive, or the clock skew insensitive technique is there, where there are two kinds of, like PMOS and NMOS are top and down, bottom. So here it's okay. So here let's assume that the clock is 0 and clock bar is 1. So by the way, this technique is C-square Mos, where the first thing is clock equal to 0 and clock bar equal to 1. Let's keep those things open. Clock bar equal to 0, clock equal to 0, clock bar equal to 1, clock bar equal to 1, and clock equal to 0. I know that whenever there is clock bar equal to 1, let's draw it here because that's better. Clock bar equal to 1 and clock equal to 0. Clock bar equal to 1, clock equal to 0. Now, by this, you can understand that because of this 1, this transistor is on. Because because of clock 0, this is also going to be on, right? And at the time, these two transistors are off. So it doesn't matter what is available. When clock equal to 0 and clock bar equal to 1, whatever D you are going to feed, the output is D bar, and it's going to be taken on the capacitor, and inversion of that one is going to be available at the Q. So when clock equal to 0, this X equal to D bar, and it's going to move with respect to whatever the input you are giving. So whatever the input is there, the complementary function of that one is going to be here. Note that this channel is created because of this clock equal to 0 and clock bar equal to 1. And when it's a reverse of that, means when clock equal to 1 and clock bar equal to 0, so clock equal to 1, clock bar equal to 0, clock bar equal to 0, and clock equal to 1. So this combination makes these two transistors in on mode and these two transistors in off mode. So at X, the value is latched, which was previously available over here, right? The last value will be here, right? And until this clock bar is equal to 0 and clock equal to 1, Q equal to D, and that's going to be kept over here. So this is a positive age triggered circuit. Now the whole problem occurs. Like, this is very fantastic thing. Things are going pretty fine. There is no problem. It's similar to what we have done over here. When clock and clock bar are not skewed one or not having the same state, till that time problem is not there. So let's see if clock equal to 0 and clock bar also equal to 0. So there are two things we are going to see. 0 0 overlap. We are looking for 0 0 overlap. So this condition is the one when clock equal to 0, clock bar also equal to 0, clock bar equal to 0, clock equal to 0, right? So all these clocks are 0. So in that case, let's see which transistors are going to be on. So you can see here, this transistor is on. At the same time, this transistor is also on, right? However, these transistors are off, right? Because they have been kept such a way that. So now what is happening? Because of this, we have actually the different diagram. So because of that, such circuit will occur and these two transistors are off. You can see here what we have done in the previous circuit. Same circuit has been redrawn where this cross marked transistor M3 and M7 have been removed. So what is happening if I am giving here D, because of this closed path, X equal to D, and its value 1, D might be 1 0 anything, right? So if it is 1, then this transistor is going to be on. However, there is nothing is available to make the connection between Q and M5. It's a high impedance state, right? So whatever is here, it will not go that side. So that was happening over here when clock and clock bar were 0 0 or maybe 1 1. The problem was D was making the direct connection with Q. However, in this case, there is no direct connection going from D to Q. Right now, X equal to D, and when it's changed the state, like going from like this one will be on, then we will have the Q equal to D. Otherwise, it will take the value whichever is coming from D to X, whereas this D value will not be transferred to Q, right? So in 0 0, there is no problem. 0 0 overlap, there is no problem. Let's look at the situation when both are 1. If both are 1, that situation is known as 1 1 overlap. Clock equal to 1, clock bar equal to 1, clock bar equal to 1, clock equal to 1. In that case, we are going to have these two transistors on, M3 and M7, whereas M4 and M8 are off. Removing these two transistors, we can have such diagram. Sorry, this is 0 0. Such diagram. In that case, whatever the D input you are giving here, if it is 1, then X equal to 0. If this is equal to 0, then this is already in off state. So X will be same as what previously it has over here. So this capacitor was already charged. So X at the previous value, or you can say that it will latch, right? So this is what happening. And in the next stage, when you can see that there is no connection from X to Q, D to X is already there, right? But X to Q is not there. Here there is high impedance state, so this X is not transferring at the Q side. So even if there is overlap, now we can make this conclusion that C-square Mos register with clock and clock bar clocking scheme is insensitive to overlap, as long as, look at this, this is very important thing over here, the rise time and fall time of the clock edges are sufficiently small. Means if by chance all four will be on, by chance clock, clock bar, clock all are on, that can happen when you are going from 1 to 0 and 0 to 1. Let's say this is going clock and this is going clock bar. So if rise time and fall time are not sufficiently small, but they are giving enough chance when there is undefined state, or maybe it's in a particular state, then all these four transistors will become on and there is a direct connection from D to Q. So in that case, it's better you should keep sufficiently small rise time and fall time. If they are not, then such problem will exist. For that, there is already one question is given in Rabi's book, and it is explaining that if it is rise time and fall time are not enough small, then you can observe that D and Q are exactly same, right? Okay. Other than that, like C-square Mos is the one which can be designed either positive edge triggered or might be negative edge triggered. So when you are making this, now what I want that a circuit which is not only sampling at the positive edge, but I want to see that at the negative edge also. This is going to reduce the requirement of the frequency. It will be in the half time I can have both the data. So what I can do, it's similar to what we have done, exactly like that, but this is a C-square Mos technique. But you can see over here there are two inputs, N1 and N2. Notably, N1 equal to VDD when D equal to 0 and N2 equal to 0 when D equal to 1. So those values will be available and that value will be feed over here. So N1 is going to be connected over here and N2 is going to be connected at the other side. And look at this. This particular circuit is working at when clock bar equal to 0 and clock equal to 1. Whereas this works at when clock equal to 1 and when clock equal to 0 and clock bar equal to 1. So it's exactly opposite of the direction of what we were doing. So during that time, whatever the D is there, so during 0, D will be sampled over here, and during clock bar, it's a latch value in C-square Mos. But if you look at other way around, during that time when that was not taking the output, it's actually taken care by this circuit. So it's a complement to each other. So that you can see here, and that is going to give you advantage that it's a faster one. Here requirement of clocks are actually driving only 8 transistors, so it's 8 times C gate. Whereas in the case of C-square Mos, of course, it's going to be the loading of the 4 times C gate. But if you're looking at the previous one, this has also the 4 times C gate. That's the capacitance the clock has to drive. Whereas if you want to not use such technique, you can use only the pass transistor where there is no transmission gate. So with one transistor each, you can have 2 C gate of the load. But in that case, it is advisable to use this circuit so that you can restore the level which you want, right? So this is all about CMOS and Square Mos technique. The next one is okay. So here in all these things, why it's happening? Because we had clock as well as clock bar, right? So all the all the gates were working on the application of two clock phases, clock and clock bar, which are 180-degree phase shifted to each other. Whereas I'm proposing a technique where there is only one clock, either clock or clock bar. If you use one of them by the usage of maybe NMOS and the usage of PMOS, I'm going to call it TSPC, which is true single phase clock. I'm not going to use another clock phase, but I'm going to have only single phase. In that case, let's assume that I'm making the positive latch and the negative latch with only clock, or maybe you can use a clock bar also if you want to make it in other way around. If you like to use PMOS with the clock bar, it will become negative, right? In this case, so this is called positive latch and this is called negative latch. You can understand its performance as follows. When clock equal to 0, what is happening? When clock equal to 0, in the case of positive latch, you can see it's like this. Notably, there is already one capacitor is already there, right? And that capacitor is coming from the fact that the diffusion capacitance of the previous gate and the gate capacitance of the next stage, generally Cox plus Co overlap, is going to be over here. So all these addition of all these parasitic capacitance are going to be here. So if in equal to 0, this node is connected to VDD. When in equal to 1, this node is going to be connected to, by the way, this one is already 1, you can see. Already 1, but still it will not make the connection to the output, right? So VDD will be staying here in that case, right? It will not go here and there. But in the another stage, when clock equal to 1, when clock equal to 1, this will make the connection and this will also make the connection. So in the previous time when clock equal to 0, both the nodes were connected to VDD. Such kind of structure is as good as we are pre-charging that node to VDD. Whereas in the next stage, when clock equal to 1, when both of them are making the connection, what is going to happen? Now it's dependent on the input data. When input equal to 0, of course, output is VDD, and consequently, if it is VDD, this transistor make on and this transistor is on over here, and these two transistors are off if in equal to 0. Right? So in that case, out equal to 0. Whereas in the case of input equal to 1, this one is off and this one is also off, whereas these two transistors are going to be on, right? In that case, the first stage output is equal to 0, and the second stage output, as this one is making the contact, it's equal to VDD, right? Similarly, you can also take care of negative latch, right? Or you can say that the the master slaves are together, and you can make the connection such that it's going to give you positive edge trigger or negative edge trigger, right? But this whole thing requires only one clock, either clock or clock bar. So in that case, such kind of structure is known as true single phase clock, where clock has to drive only two gate capacitances. So that way it is pretty fast, right? Now, adding to the TSPC, we can add the logic also. So what I'm doing here is, this is a good technique. Let's work it on only on clock side. So in that case, you can have power up network and power down network as we used to make it. And in between this output and just above power down network, you can have the clock. And this one is, let's say, inverter, or the second stage, which is collecting the data. So in that case, what is happening, when clock equal to 0, let's assume that when clock equal to 0, in that case, no matter what the things are, but Q is recharged to VDD, right? So that will be staying there. Now, when clock equal to 1, it will give chance to travel the digital logic 1 or 0, depending on what input you are giving to power up network and power down network. So let's assume one technique where you are using the AND gate. So AND gate has, this one is power down network, and this one is power up network, right? So in that case, what is happening, when clock equal to 0, it does not make any sense over here. But when clock equal to 1, what is going to happen? So now, depending on inputs, like when both the inputs are on, then output is 0. Otherwise, the output is actually VDD. And that is the time when you are going to have logic 0 out over here. And after this, as this is 0, this transistor make connection. This clock is already on, whereas this one is not going to make any connection. So Q is going to be equal to VDD, right? So this is what we are doing here. In the case of TSPC, we can add any kind of logic as well. Now let's talk about some other technique where you are not taking the output exactly from this node, only from this node, but you are taking the output from two different nodes, which are going to be known as split output. So if it is positive latch, you can also note that there is only one true single phase clock, and right now in this structure, only one capacitance of the gate has to be driven by clock, either in positive latch or negative latch. Whereas in the case of previous thing, one transistor was more, right? So what is happening, let's see. If clock equal to 0, let's start with the clock equal to 0. So if clock equal to 0, this is off. In that case, if in equal to 0, then this node is connected to VDD, and this node is equal to 0, right? This is happening because this is, by the way, this is the previous value. You cannot have only 0, it depends. Okay, initially where it was charged. If it is charged to VDD, then this will go to 0. Otherwise, no. Now, the interesting thing happened when the clock is equal to 1. If clock equal to 1, it's going to make the connection from here to here. Okay, now let's start with the playing with the input. So if input equal to 1, or sorry, input equal to 0, it will make the top transistor on, and here you are going to see VDD, because this lower transistor is already in off state, right? And if this is VDD, now this connected to the value depending what value was here, right? Or it will actually hold the value which was previously, right? It will hold the previous value. I would say that it will hold the previous value. Now let's forget about this. Let's assume that if in equal to 1, in that case this is in off state, but note that this value was at VDD for your information, right? This value was at VDD. Previously I charged at VDD, and when in equal to 1, fortunately it makes connection, right? So in that case this VDD will go to 0, right? And accordingly we can move, and accordingly this is 0, so output is actually VDD. But if in other way, whatever was the previous value over here, accordingly you can have the output. So you can observe that and you can find out if there is any problem associated with this one. And with this technique I am leaving to you people. If there is any problem, you just find out. I'm not going into that, but if you can find out, that is good, right? There has to be some problems. If it is there, you just list down. Now there is a silver bullet that's similar to the Square Mos latch. The TSPC latch malfunctions when the slope of the clock is sufficiently steep. Slow clocks are not good, cause both NMOS and PMOS clock transistors to be simultaneously, means there is a clock skew, and in that case you will see bad output, right? But in that case you can have the undefined values of the state and race condition. You can see now, you can understand what is race condition is also, right? So you have to make sure that clock slopes are sufficient enough so that you can control it and you can have the output as it is required, right? Okay, so that might be sufficient for the dynamic latch or flip-flop. Where there are two we have following things we have studied. One with just a master slave, where you had the transmission gate and then you're connected to the capacitor. And later on you made such a circuit one by one, and such a way that one is clock, one is operated with clock, and next one is operated with the clock bar. Next one, we have studied that there might be the case that there is a clock skew, and clock skew has been solved by Square Mos. And afterwards, we found out that there might be the case where you have to drive the 8 gate capacitances. So 4 gate capacitances. If you want to avoid those, you can use TSPC, true single phase things, where you are going to have two gate capacitance to be driven. And if you don't like this one, you can have also the last one, where you have to drive only one capacitance of the transistor. So all these things we have studied, and all these things we have understood in terms of changing the clocks and clock bar. Next thing is going to be with the pulse resistor. We are going to make the dynamic latch. Okay, so that's all for today.